good. All right, to find that out, all we have to do is go to our Canvas and look at the schedule of lectures and exams.
I just looked. It looks like it's on the 6th, so next week.
It should be next Wednesday. I mean, next Thursday. Yeah, it's next Thursday with our updated schedule. And we should be getting through chapter 11, most of it today. No, we'll be doing chapter 11 on Thursday, so we will have time for a review. So I think that's going to be good. Don't forget, homeworks are due for chapter 11 is actually due after the exam. I need to change that. It needs to be due before the exam so you can review. I'm going to make the chapter 11 homework due on the 30th so that you can have it available to you for the exam. Okay.
Exam 2's on Tuesday, correct?
It says on mine the 6th, which is the following Tuesday. Yes, you are right. Okay, exactly where it is. I can leave it exactly where it is. That's right. It's actually a week away. So we have one more Tuesday of lecture, and then our exam is going to be on the following Tuesday. So it's a full 2 weeks away. Wow, 6th already. All right. So that's not too bad. Okay, so welcome back to 2330. We're going to continue on with doing those goal slides the way we were using them, and then that'll get us to have a little bit of breathing room with our other thing. It's in a week from today. Yes, a week from today. Sorry. So we're going to get through chapter 11 today, March 30th. Right now, we're going to have time for the review on Thursday, and then our exam will be on the 6th, which is for the following Tuesday. Yeah, I think I finally got that right. Okay. Okay, so I'm going to go ahead and share my screen, and we're going to talk about the last thing in amines. Okay. So we had, when we were talking about amines, we had a thing that, they are labeled a little bit differently. They're labeled by how many things are attached to it. So a secondary amine has 2 carbons attached to it. So that was a little different. We learned that they could be used as bases, and we learned a little bit about base strength in the last section as well. And now we're going to learn a few reactions. We have very few reactions we have to do with amines, which is why the homework is so short. But what you should focus on is the basicity of the amines, the nomenclature of the amines, and these reactions of the amines. Okay, so we're going to do reactions here. So the first thing that we do, because they are bases, they react very strongly with strong acids, and then they become water soluble. So this is norepinephrine, which is used, I believe, in a nasal spray application here. It's very poorly soluble in water. We don't have enough hydrogen bonding to pull in all those carbons, and so it's poorly soluble in water. However, with just one equivalent of acid, it turns it into the ammonium salt. The ammonium salt is highly water soluble. Okay. There's another analogy to this in the fact that cocaine, as the powdered form, is actually the sulfate salt of that compound, and it is water soluble. But if you remove that sulfate by using a base, and then it is no longer soluble in water and comes up and crystallizes on the surface, and that's crack. So, but don't use either one of them. But that's just another example of how HCl can make an amine, especially a water insoluble amine, into a water soluble amine. Okay, so the other thing to note is that when we talked about benzene reactions, we never actually were able to put a nitrogen with 2 hydrogens on the ring. All we could do is nitrate it because our mechanism required a positive charge. Okay, so you can't directly put an amine on a benzene ring, but you can do a reaction where you have created your nitro compound that you have, and we can do a catalytic reduction using hydrogen gas and a catalyst like nickel with platinum under a little bit of pressure, and it will generate our free amine and 2 equivalents of water. Notice that's why we had to use 3 equivalents of hydrogen, because we're getting 2 equivalents of water and our free amine. Okay, this reaction works very quickly. You just shake it in the bottle for about 30 minutes and it's done. Okay, so that's one way to create a primary amine from an aromatic system, is you could convert the nitro group to the amine. Okay, the other thing we have is we learned that amines are Lewis bases, and therefore they are nucleophiles because they have a lone pair. Okay, so it acts as a base to acts as a nucleophile to react at our carbon center, which is our electrophile, and it can generate initially this formation of this ammonium ion with now 2 carbon bonds to it. The original amine only had 1 carbon on it. There we go. And 1 carbon on it. So this is our primary amine. And then when it does the displacing the chloride and forms this, we now have a secondary amine. Okay, so that's the first thing that happens. But what can then happen is it can lose HCl to a stronger base, and it becomes a nucleophile again. Okay, so if a base comes, if a base like this comes around and deprotonates it, we now have a secondary nucleophile, but we started with a primary nucleophile. Okay, so what can happen? Well, it can react with another equivalent of our leaving group because it connects as a nucleophile. And so it's going to happen again, and then we're going to lose a proton, and then that's going to give us a tertiary amine. And then it can still act as a nucleophile, and therefore it can give us our quaternary ammonium salt. So what this means is it's very hard to use an amine as a nucleophile to stop at a primary, a secondary, or tertiary amine. You will always get a mixture of these. So we have to have a strategy to do this so we don't have this mixture of products in our reaction mixture. And so we have a way of doing that by not using it as a nucleophile, using some other reagent, like converting it into an amide and then reducing that amide down. That would allow us to easily get to that secondary amine. Okay. Questions on reactions on amines? That's all we have for reactions on amines.
Could you go back a couple slides, please?
Yes. This one?
One after that one, please.
Up?
Down.
Down. All right. Here we go. Okay. So in this particular one, we have our primary amine acting as our nucleophile to displace chloride and create our intermediate, which is this protonated form here. If this loses HCl, it regenerates the lone pair, which turns it back into a nucleophile.
All right, thank you.
Okay. And then it'll just keep going and going and going until you have a horrible reaction mixture. Okay. All right, questions on reactions on amines. Okay. That's why the homework's so short. It's a kind of a short chapter. All right, so what I'm going to do is I'm going to start our next chapter, chapter 11 now. And chapter 11 is broken down into 3 different goals here. We're going to talk about 3 things when we talk about spectroscopy. The 3 things we're going to talk about are IR spectroscopy, which is infrared radiation, and the important parts of that we'll have to see. Then we're going to talk about NMR spectroscopy, which is nuclear magnetic resonance spectroscopy. And we can do that with the hydrogens on an organic system or an isotope of carbon that's heavier than regular carbon in that isotope. And I'll discuss each of those and what's important about reading each of those things. But let's start with IR spectroscopy. So electromagnetic radiation comes in a lot of different forms. We also know it as light. Light is a thin band of that electromagnetic radiation, but it goes all the way to cosmic rays and all the way to heat. Infrared radiation, it'll go down to radio waves, it can go to microwaves, which are smaller. So we have this broad range of different things that are in that electromagnetic spectrum. But the things we have to think are important here is the wavelength. Now, the wavelength is the distance, because electromagnetic has a wave component and a particle component to it. It's in this wave. And so if we look at the peak of one wave going through the trough and the peak of the other way, that distance from those two peaks is what we call the wavelength, okay? And the wavelength can be related to frequency because the frequency is number of waves per unit of time. And in this case, the unit of time is a second. So that's the number of times it moves up. It goes from peak to peak to peak to peak during a number of seconds. And the unit we use for that is called hertz, okay? It's either the HC or it's reported as S to the -1, which is 1 over S. So it's per second, okay? So per second. So those are important to know because that range of what the electromagnetic radiation is useful for changes based on the frequency, okay? So let's look at that broad band. Again, this little teeny band in the middle where our wavelengths are very short, 7 times 10 to the negative 7 meters, 4 times 10 to the negative 7 meters. So that's very small. This is the little bit of the band we perceive with our eyes, okay? We can perceive a little bit of the IR radiation with our skin. We can feel the IR radiation warming our skin. We can perceive the UV radiation when we get a sunburn, okay? So those are the bands of light that we can perceive with our physical bodies. However, there's a whole bunch of other things we can do. By going up to a higher frequency right here, we can get to X-rays and then all the way up to gamma rays. And notice this is the wavelengths are getting smaller and the frequencies are getting bigger, okay? So as the waves get closer and closer together, there's more of them that can happen in that 1 second. So frequency gets bigger, the smaller the wavelength we have. Okay, now let's look at the other side. If we go from IR, we can go down to microwaves, and the microwaves make certain bonds move and vibrate. In fact, at 2.45 gigahertz, that is where the OH bond vibrates in. And that's why your food heats up in the microwave because it has water in it, and the water is the part that does that. Then we can go to slightly longer waves, and we have AM and FM radio. And then these are long wave radios that are like, look at this, 3 times 10 to the 8th. Okay, so that means that that is over 30 kilometers long from peak to peak, okay? And so the number of times it can vibrate in a second is only 10. So that's why it's really long wavelengths here. So again, we want to talk about this little section here, IR. And the reason we want to talk about IR is because it does two things for us. Number one, it gets absorbed at different energies to cause vibrations in molecules. Okay. So when we talk about IR spectroscopy, we're talking about a small section of that. It's typically from 2.5 to 10 to the minus 6 meters to 2.5 to 10 to the minus 5 meters. So we only have one order of magnitude going from that. Okay. Now, because that's kind of hard to write on a slide all the time, they decided to take the reciprocal of it. So it's 1 over that 2.5 times 10 to the minus 6 to give us what we call reciprocal centimeters. Notice these are in meters right here, and these are 1 over centimeters. Okay, we call that a wave number. Now, the great thing about converting it into wave number is the idea that we now have a nice convenient band to look at. We look at from 4,000 wave numbers to 400 wave numbers. And so we just have that range where we look at different absorptions of that IR radiation in our molecules. Okay, so this is the most important slide on goal 1, okay? And knowing the trend that you see here will make it easy for you to pick out which functional groups could be in which bands, okay? So notice we're going from 4,000 wave numbers to 400 wave numbers, and I've broken it into 4 sections, okay? So we have one at 2,500, and so we have only certain things vibrate in this range. We have the 2,500 to 2,000, only certain functional groups vibrate in that range. We have another section from 2,000 to 1,500, only certain things vibrate in that range, and then the last one here. But what I want you to understand is the trend that they have. When you have a heavy atom and a light atom, it can vibrate faster because the light atom takes less energy to move. Therefore, all the high frequency bands all involve a hydrogen attached to a heavier atom. Hydrogen on carbon, hydrogen on oxygen, hydrogen on nitrogen. So the only thing that shows up in this area is the carbon hydrogen bond, the oxygen hydrogen bond, and the nitrogen hydrogen bond. Okay. So because it's heavy and light. Okay. Now, so because that is a high frequency, it can vibrate really well. So what would be the next highest frequency? The next highest frequency would be a very strong short bond. So the strong short bonds are our triple bonds with carbon and our triple bonds with nitrogen. So that's in the next higher frequency range, that middle band between 2000 and 2500. So if you have an absorption in that range, that means you have that particular bond somewhere in your molecule. Okay. Now, if we move down from 3 bonds to just 2 bonds, that's where we see our next thing. We have a carbon-carbon double bond, a carbon-oxygen double bond, and a carbon-nitrogen double bond. And this is between 1500 and 2000. And these can shift around a bit based on what's attached to them. And I'll tell you about that when we talk about specifically about the carbonyl. We'll move it up and down based on what's attached to it. And then those weakest bonds, are going to have the lowest frequency, are going to be the single bonds between heavier atoms. So notice no hydrogen is down there. It's all carbon-carbon, carbon-oxygen, carbon-nitrogen, and carbon-halogen. Gosh, mold messed me up today. Okay, so if you have to memorize anything about IR, remember this chart. Okay, it'll help you understand the system. Yes, you have a hand up.
If you have more than one of these things, do you just see more than one thing then?
Yes, because notice I'm not saying individual compounds show up here. I'm saying individual bond types. So if you have something absorbing in this region and this region and this region, it means that you have at least one carbon-hydrogen, one carbon-carbon triple bond, and one carbon-carbon or a carbon-oxygen double bond. So if you have a peak in each of the zones, that means that functional group is represented in your molecule. That was a good question. All right, so let's show you how that works here, okay? Let's first just take a look at the compound here. Okay, what kind of functional groups do we have? Well, we have carbon-hydrogen. We have a double bond with an oxygen. We have a double bond with a carbon, and then this, of course, has that. And then we have an OH, okay? So that means we should have 2 types of things in the hydrogen band, that above 2500. We're not going to see anything in the 2500 to 2000 because we don't have any triple bonds. So we're not going to see anything there. We are going to see something in that 1500 to 2200. And then we'll probably see a bunch of other things for this carbon-oxygen bond here, this oxygen-carbon bond here. Those will show up somewhere else. That's where the stuff that's going to show up below 1500. Okay. Now, notice how busy this below 1500 is. Okay. We call that the fingerprint region. Okay. It's hard to identify individual functional groups in that fingerprint region, but what's good is that you can take a spectrum and you can get a database and you can match all those peaks to the same, to other things using a computer. And you can say that, yes, I absolutely positively have this because all of my peaks in the fingerprint region work. It doesn't really help you identify functional groups because it's so noisy down here. We're not going to worry about that. So let's look above 1500 to help us see if we see all of these different functional groups. Okay. So the first thing we see is we have this big peak right here. And what we're going to see is that this is actually our OH peak. Okay. It can be up here as well if it's in an alcohol, but it's always going to be big and broad. Okay. And it's because of hydrogen bonding, and I'll describe that a little bit more later. Then the next thing we see above the 2500 right here is we get peaks here and peaks here, okay? So notice that this is percent transmittance. So this is transmitting 100% of the light, and this is transmitting 0% of the light, which means there's no functional group absorbing until we get to that OH group. And then these sharp peaks right here are going to be our carbon hydrogens. And we had a couple different kinds of them. We had one on a methyl group. We had one on a benzene ring. So we're going to see two different peaks there. And we're going to see that they show up in slightly different regions. Remember I said we didn't have anything in the triple bond region? So this space is empty. There's no peak in this area. So we don't have a triple bond of some kind. And then the next thing we see is one, two, three peaks here, okay? So what could that be? Well, this is a CO, which could be one of the peaks. This is a different carbon-oxygen double bond, so that's going to be one of the peaks. And this double bond is going to be one of the peaks. So we have three different peaks because we have three different types of double bonds, okay? So that's how to read our spectrum for that and what we're looking for. We're looking for, is that functional group present? And what functional groups are present? And then you have to string them all together. If something is missing, it can't be that compound. Okay. So we have different intensities and different widths of lines based on the type of functional group. But I can give you a general trend on that, okay? If we have an alcohol, OH, it's of course going to be above 3000, but it's going to be broad. It's going to be broad like this, and it typically is a little bit above 3200 if it's an alcohol, okay? The reason it's broad is because of hydrogen bonding. The number of hydrogen bonds that OH has to its neighbors determines how fast it vibrates. And the fact that hydrogen bonding is very dynamic means you have bunches of different types of hydrogen bonding all at the same time. That broadens out our peak. Okay. So the next thing we have is slightly lower. It goes across that whole range and dips down all the way down to almost 2400 sometimes. And that's the carboxylic acid peak, the carboxylic acid peak. And just think about that. That carboxylic acid is also broad because it hydrogen bonds. Okay. The next peak we have is a light atom with nitrogen here, and that tends to give a medium intensity peak, but it's usually fairly sharp, something like that maybe, or maybe a little smaller right here. The next three peaks are very important. These are the different types of hydrogens we find on carbon. If the hydrogen is bound to a carbon that's triple bonded, it's the highest frequency, okay? It's the highest frequency. So we're gonna look for something like this right here. Could be that hydrogen on that double bond, okay? Because it's the highest frequency of the set. So this is sp hybridized, and it's the highest frequency. Now, if we look at a double bonded carbon here, we're gonna see that in another range, but we have a hydrogen here, and this is gonna be next over. This is going to be just above 3000. So we're looking at just above 3000 to 3100. And then notice that when you have a single bond, an sp3 hybridized carbon here, it's just below 3000. Okay. So that means we have three ranges. We can see whether we have an alkene, an alkyne, or an alkane just by looking at this peak here. So the peak below 3000, notice this is below 3000, means this is an sp3 hybridized carbon. This is above 3100, so that's probably got a triple bond on it as well. Okay, so, but just because we have a peak here doesn't definitively mean we have that triple bond. We must also have the peak in that 2000 to 2500 range. And in this case, we do. Notice this is not as strong a bond as our alkane peaks here. Think about that. The carbon and hydrogen, the hydrogen's very light and vibrates very quickly. But now we have a triple bond, And, you know, electronically, it's not as polar as the carbon hydrogen bond. And so it's going to absorb less strongly. And because it's such a high vibration, it'll also be fairly weak. Okay. So think about the polarity of this. There's no, both sides of this are basically neutral. There's no polarity to the system and gives us a weak peak. In contrast, when we have a carbonyl peak, that's a very polar molecule. We have a partially positive and partially negative side, and therefore it gives us a strong peak. So that polarity gives us a more intense peak. And so that when we go back to the alkane right here, the alkene, we again have less polarity and it's a weaker peak. We go to the single bond with carbon here, and we get a strong peak again because carbon and oxygen have different electronegativities. So let's kind of string those together in what we see here. Well, we'll get to just below 1500 here. We have a peak for a triple bond. We have peaks for aliphatics, and we have a peak for a hydrogen on an acetylene. So what that means is we have acetylene, but it has a hydrogen on the end, and then we have some chain on it. Okay. No other functional groups are present. There's nothing else here, which would be the carbonyl peak or the double bond peak. And so we know just from the peaks that are present, this must be an alkane with a alkyne with a hydrogen on it. Okay. So let's go through each of the functional groups and watch them change by their IR signature. Okay. So the first thing we want to look at is the alkanes. So think about the bonds we have available to us. We have a carbon-carbon bond. And so that's going to be just below 1500. Okay. And we have a carbon-hydrogen bond, and that's going to be just below 3000. Okay. So let's look for those peaks and see if we see anything else. Okay. So we have our carbon-hydrogen bond right here. And notice it's below 3000. All alkanes are below 3000. Okay, so that's good for us. And then we have a medium peak here, and that's our carbon-carbon single bond right here. And then way down here, this is in our fingerprint region. And it turns out this is going to be an actual lagging motion for that. And that's why these are harder to understand. And so that's why we rarely assign them. But we have our carbon-carbon single bond peak here. We have our carbon-hydrogen bond here. And we have no other functional groups present. Okay? Because there's no other absorption. All right, so what if we change it up a little bit and go to an alkene? Okay. If we get an alkene, we now have a new functional group, right? We have our carbon-carbon single bond. We have a carbon-carbon double bond. We have a carbon hydrogen that's on that aliphatic system, the alkane, but we also have a carbon hydrogen on the alkene. So that means we need to see at least 4 different peaks to show that we have this. So let's blow that up and look at it. So the first thing we notice is if we look at 3000 here, we have a peak above 3000. So that's the hydrogen on the double bonded carbon. Okay. Then we have peaks below 3000, and those are the hydrogens on the saturated carbons, the ones with have sp3 hybridization. Then the only other thing we see above 1500, here's our 1500, is a weak carbon-carbon stretch. Okay, notice no other vibrations available to us, but the indication that we have one peak above 3000 and one peak below 3000 tells us we have an alkene and an alkane present in our system. And this particular one is this little thing right here. And notice how busy the fingerprint region is. It's kind of hard to identify. So again, look for the functional groups above 1500. Okay, now let's switch to an alkyne. If an alkyne, we're going to move that carbon hydrogen peak up again. So notice we're going to blow it up and look at that 3000 mark. All right. So the alkene showed up about right here. The alkyne shows up higher. Notice that's 3300 now. So we're going to see that higher peak. So we have at least an alkyne hydrogen, and we have alkane hydrogens. But to prove to ourselves that this is not something else, we have to have that carbon-carbon triple bond. And we do. It's right in that 2,000 to 2,500 range. Excuse me, I thought my cough was getting better. But then right here is our 1,500 range, and that's where our single bonds are going to happen. We have nothing in this range. So the only functional groups we have are an alkane hydrogens, an alkyne, and an alkyne hydrogen, which means we can then say, okay, of the choices I have, we have an alkyne hydrogen, an alkyne, an alkane, and alkane hydrogens. Therefore, this is my compound. Okay, so that's a neat little thing showing you where those hydrogen peaks walk along the, they move up and down the spectrum based on what they're attached to. Okay, so now let's talk about alcohols. That's another functional group that shows up very well in IR. The first thing we're going to notice is this big, broad peak here. Okay, so it's big and broad because of hydrogen bonding, and the intensity varies a little bit. So it can be maybe up here sometimes, but down here. But the idea is that it's above 3,000 and it's very broad. And again, we draw a line on our 3,000 mark. We only have hydrogens on carbons that are sp3 hybridized because we have no other sharp peaks above 3,000. And then we go nothing, 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 nothing. Here's 1,500 mark, which means we have no triple bonds, no double bonds, no carbon oxygen double bonds. Everything else is our carbon oxygen and carbon carbon bonds down here. So that means we have an alcohol with just an alkane. Okay. All right, is this starting to make sense? We're starting to, you're looking for the things that are there and excluding things that aren't. Okay, so if we take our alcohol and convert it to an ether, the OH peak goes away. Okay, there's no hydrogen bonding available to it as the ether because now you have two bonds to the oxygen by carbon. Okay, but again, we have no peaks above 3,000. Those would be alkenes and alkynes. So we have an alkane with an ether. And if we draw the line at 1,500 again, we see nothing there. We draw the line at 2,000 and 2,500. So this is our hydrogens. This is our triple bonds, our double bonds, and our single bonds. And so we can't have a triple bond or a double bond in our system. And therefore we have just a simple little ether. Okay. Okay. And notice there's also that strong carbon oxygen bond way down here. Those tend to be fairly strong because it's a polar bond, but again, it's sometimes hard to recognize. Okay. Now amines are funny because it depends on how many hydrogens are on the amine. Okay. If we have a primary amine, you're going to have two absorptions. Okay. So one for each of the nitrogens, each of the hydrogens. Okay. If you have a secondary amine, you have one hydrogen on it and you'll have one peak in the hydrogen region. And if you have no nitrogens on your amine because it's a tertiary amine, you have zero peaks in that hydrogen area because you don't have a hydrogen nitrogen bond. So let's look at that. So knowing that and looking at right here, we're going to draw our line at 3,000 again. Okay. We have a peak here. It's kind of broad, but it's not that big broad peak for an OH group. Okay. It's a little bit broad, but it's not as broad as an OH peak. And we have two peaks on it. This is telling us we have to have two hydrogens on that nitrogen. Okay, so those two peaks tell us a lot about that. We also have nothing above 3,000, so we don't have any double bonds. And so we only have carbon hydrogen on single bonded systems. Now we draw our line here, right here, and we're starting to get a peak here, okay? This is a peak for the carbon nitrogen bond. It's a little bit above here, but it's not very big, okay? And then this is also a carbon-nitrogen bond. So the fact that we have not a strong peak, the carbonyl we're going to find out is a very strong peak in this region. We don't have a strong peak, and so this is probably a carbon-carbon bond as well. Okay. So the key here is the nitrogen number of peaks changed on how many hydrogens on it. 2 hydrogens, 2 peaks. 1 hydrogen, 1 peak. 0 hydrogens, 0 peaks in that above 3000 range. Okay. So let's add a new functional group to our system here, the C double bond O. The C double bond O is always a strong absorber. Okay, it's always going to be one of the strongest peaks you'll see in your system because it's such a polar compound. Okay, but that can range from around just below 1700 to almost 1800. It moves around based on what's bonded to it, and we're going to see it move up and down based on that. Okay, so in this case, let's go ahead and blow up our region here. Draw our line here. Nothing above here, so we have no alcohols, no alkynes, no alkenes, and no amines. Okay, we only have aliphatic carbons here. And if we look here, we have a nice strong peak above 1500. This is a typical shape for a carbonyl, very nice, very sharp, very strong. Okay, and then we only have peaks below that. So our only functional group is a ketone on an aliphatic system. And if we look at the structure here, the ketone is here, and all the rest of this is the hydrogen peak we saw at here, and the carbon-carbon single bonds we see here. Okay, so that's a ketone. But what about an aldehyde? Okay, oops. With an aldehyde, what we're going to see here is that if we had an aldehyde, we're actually going to have our carbon hydrogen peak is going to be the lowest carbon hydrogen peak we have. It's right here at 2750. There's going to be a small peak at 2750, indicating we have an aldehyde. So that's how you tell the difference between a ketone and an aldehyde. You get this peak in this region here. So let's go to another functional group that contains a carbonyl, the carboxylic acid. But now we have a lot of things, right? We have a carbonyl, so we're going to have a very strong peak right there. We have an OH, so we're going to have a very strong peak right there. And then we're going to see what other functional groups are available to us. Okay. So notice this OH peak. For carboxylic acids, it tends to dip below 3000. Most alcohols are above 3000, but the carboxylic acids dip below 3000. Now notice it's overlapping the peaks for the carbon hydrogen there. So it doesn't intensify or change the absorption intensity of it. It just overlaps it because the energy is being absorbed by both of the functional groups. Okay, so, and it can only absorb so much energy, so it doesn't actually add on to it. So it looks like it's being covered up. So you can see it just right there. Okay, the next thing we see above 1500 is a strong carbonyl group. And the strong carbonyl group is right around 1700, maybe a little higher as the carboxylic acid. So what we're going to see is that the carboxylic acid is lower than the aldehydes and ketones. The aldehydes and ketones were higher. Come on. Notice the aldehydes and ketones were 1700 to 1780. So they can be much higher. So all right, so we have a functional group that has a carbonyl and a strong OH peak. Let's get rid of that strong OH peak by turning it into an ester. Okay, when we turn it into an ester, the big peak goes away. Our carbonyl changes space. Notice our carbonyl shifted up. It was at 1700 to 1720 with the carboxylic acid, but it shifted higher, 2335 to almost 1800. It can be anywhere in that range. And we have no OH, so we know we've done it. You know, this would be a great thing to do in lab, right? You can watch for functional group transformations. We could have started with an alcohol and then oxidized it to a carboxylic acid, watch that OH peak move down. Then we could have taken that carboxylic acid and turned it into an ester and watch that OH peak go completely away. So we can watch for that functional group transformation. And if we oxidized a secondary alcohol, we would end up with a carbonyl compound instead of an alcohol, and we would see that new functional group grow in and the old functional group leave. Okay, so amides have a carbonyl bonded to a nitrogen, right? But it follows the same rules as as the amines do. If it has 2 hydrogens on it, it'll have 2 peaks in the high range. If it has 1 hydrogen on it, it'll have 1 peak in that high range. If it has no hydrogens on it, it won't show up there. So what if I told you this was an amide, but there are no peaks up here? What that means is that you're going to have 2 groups with carbons on them attached to your nitrogen and no hydrogens. Okay, so let's look at our 3000 again. So we only have aliphatic peaks. We have a carbonyl peak. And this carbonyl peak, notice, is below 1700. Okay, aldehydes and ketones are 1700 to 1720. The carboxylic acids, the carboxylic acid is 1700 to 1720. The aldehydes and ketones are 1735 to 1800. Amides are below 1700. So that's a good way to look for that functional group in your system by having that carbonyl peak shift around a little bit. And in this case, we have no hydrogens on our amide, but we do have a nice strong carbonyl. Okay. If we were to look at one of the primary amides, we have 1 hydrogen, so we're going to have 1 peak above 3000. And notice its shape, okay? It's not broad like an OH, it's fairly narrow, and it's about a medium intensity. But look what happens over here is that the carbonyl is shifted way down, right up against the 1600 mark, and it's starting to get interwoven with the carbon-carbon double bond. That's what the peak above 1500 is. Here's 1500. Let me erase my scribbles. So we have a peak for the carbonyl, but we also have a peak for the carbon-carbon double bond. So that's going to tell us, hey, we have at least a carbon-carbon double bond, so that must appear in the product or in the final molecule we're trying to identify. All right, so if we have a primary amide, we're going to see 2 peaks. Notice that it's a little bit broader. It's still not as broad as an OH, but we're going to see those 2 peaks above there. And we have a good, strong carbonyl here, and then nothing else above. So we have an aliphatic primary amide. Something I wanted to look for up here is there's a little teeny bit of peak above the 3000 mark that would account for the hydrogens on the benzene ring. Those didn't show very well. Okay, so what I want you to know about IR. When you're using IR to identify a compound, if there's an absorption there, that functional group, that type of bond must be in your final product, okay? And so if you find I have a carbonyl, I have an OH group, I have this, we can tell the difference between a carboxylic acid and a carboxylic acid with an alcohol on it, or a ketone with an alcohol on it, because of the shape and position of that OH peak. So you can start to deduce by saying what is there and what's not there and identify by IR. All right, questions about IR? So what I would suggest is you devote these kind of bands to memory right here, because this is where you're going to be able to do a lot of your first guesses are on this particular page. The next thing I want you to do is remember that where the carbonyl shift going from aldehydes and ketones when they go to carboxylic acids and when they go to amides. That shifting carbonyl compound is a strong indicator of what functional group you have. Okay. Questions on that? Okay, well, let's move on to goal number 2. Goal number 2 is what we call NMR, or proton NMR spectroscopy. Okay, so we need to talk a little bit about nuclear magnetic resonance and why the hydrogen is the one that is active to this type of spectroscopy. Okay, the first thing we have is the idea is that we're going to have a molecule, and the molecule we're going to induce using magnets a ordering, and then we're going to watch it relax back to its normal state, and when it does, it gives off a signal. Okay, so that's what we're going to do, and we're talking specifically about hydrogen and carbon. Notice that hydrogen has an odd numbered isotope 1, and the carbon has an odd numbered isotope 13. That becomes important. Okay, so the reason we have that is that you have an uneven number of protons and neutrons in your nucleus. Okay, if you have like all protons and you have an even number of protons and neutrons in the thing, they can balance out to where they were countering each other's magnetic fields. So if we only had 4, 2 of them would be positive and point north pointing down, 2 of them would be north pointing up, and they cancel the signal out. Okay, so but by having that odd number of things spin means we have what we call spin. We haven't canceled out all our magnetics. We've canceled out all our magnetics but 1. And that canceling them all out but 1 is the one we see when we do this. So you must always have an odd number in your isotope to have to be active in carbon and proton NMR. Okay. So the next thing we want to talk about is resonance. Okay. So when we talk about electromagnetic radiation, it has a electronic component, it has a direction, it has a wave, but as it goes, it also has an electric component and a magnetic component. It's called the right-hand rule, where the magnetic component is going to be, the electric component is going to be orthogonal to the direction of the thing, and then the magnetic field wraps around it as it goes out there. So light has that electromagnetic part. The electro part is going one direction, the magnetic part is going the other direction. So if there's magnetic part in the radiation, then we can take that mismatched set of spins in the nucleus and be able to sense them. So the first thing we're going to do is we're going to align them in a magnetic field. So they're going to try to cancel each other out as much as possible. The ones that can't cancel each other out, when we hit it with a radio frequency, it flips it to a higher energy state. Okay, and so it flips it to this high energy state. And when it's in this high energy state, it will eventually relax. And when it relaxes back, it gives off electromagnetic radiation that we can sense with the detector. Okay. So we pulse it, it flips upside down, and then we wait for it to flip back. Okay. So the time it takes for it to flip back changes based on the electronic field around that atom that we are doing. Okay. So let's say we have this right here. This is called TMS, tetramethyl silane. Okay. Now the silicon carbon bond, the silicon is more electronegative than carbon, so it has an interesting interaction. It changes the speed at which these carbons and these hydrogens will relax. In fact, we use this for our standard in all of our systems. So we were always going to say TMS is 0 in a proton NMR, and TMS will be 0 in a carbon-13 NMR. So we just set it as arbitrary 0 because most things are above that. Okay, so we're going to set that as our standard. That's the one that's going to relax the fastest, and it's going to relax first. So we're going to look at that as our 0 mark, and it's going to be above or below that mark. Okay, So how do we do this? Well, usually we take a superconducting magnet. Usually there's a big thing around it with liquid helium and liquid nitrogen in there. And then what we're going to do is we're going to have one set of coils that pulses the sample with electromagnetic radiation. And we're going to have one set of coils that listens for them to relax. Okay. And it's going to emit another radio frequency. And that time it takes to emit that number of frequency is how we get our NMR. Then we have our sample here. What's interesting is the sample has to be a liquid and it has to be spinning at a certain rate to make it homogeneous as possible. Trying to mix in any inhomogeneities in your solution by just spinning it. Okay. So it involves magnets, it involves radio frequency, and it involves listening for them to relax back to our system. So what does that look like? Okay. So when we analyze an NMR spectrum, a proton NMR spectrum, we have to think about 4 things, okay? And the 4 things that we need to do are look at the number of signals we have, the intensity or the number of equivalent hydrogens that would be under that peak, that position of the peak, different positions relaxed at different times and therefore have different functional groups on them, and then spin coupling, and that's the hardest of the set. So let's go through these one by one and look at an NMR spectrum and identify the number of signals, the intensity of the signals, the position of the signals, and the spin coupling of that. It's easy to remember as spin, so you have spin, position, intensity, and number. Okay. So let's go through those one by one. A typical NMR looks like this, okay? And when we have it, we have intensity. Now this intensity is a relative intensity. We don't have an absolute number for it. So this is just a relative intensity of there. We usually kind of scale it to get as good a picture as possible. On this one, notice we have TMS here. That's what our reference standard for 0 is. So it's included in the experiment, so we know exactly where 0 is. Okay, so we have, let's see, number of signals. Okay, we don't count our TMS as a signal because we put it in there so we know where 0 is. So now we have one signal here and one signal here. So in this case, we have 2 for N, for our number of peaks, okay? So let's see, it's number intensity, okay? The intensity is not the value of the height itself. The intensity is actually the area completely under the curve. And we call this an interval. We're gonna actually sum up all the area under the curve. And what we're gonna see is the ratio from one peak to the next peak is equivalent to the number of hydrogens on that peak. And I'll show you that in a minute. The next thing, let's see, Ni, so we have number, intensity, position's next, okay? So we put our 0 in there so we know that. So this one's shifted up this much, which means that one relaxed first. Then this one's shifted up this much, which means it relaxed second. And we have nothing else relaxing up here, okay? So that's our position peak, okay? So we have number, intensity, which is the area under those peaks. And now we have spin coupling, okay? So that's what this looks like. This is spin coupling, and the number of peaks that you find in a particular position tells you something about how many hydrogens are on the adjacent attachments, the carbons or whatever. So we're going to find out that this is a certain number of hydrogens nearby, and this is a different number of hydrogens nearby. So that's that spin splitting that we're going to talk about. Okay, so that's how we identify all the different parts of our NMR. So the next thing we have to do is figure out how many signals we're going to have. And we can predict how many signals we have by looking at the number of hydrogens that have the same chemical environment. What do I mean by same chemical environment? If you were trying to number it and you could number it such that any one could be the starting point because they looked the same. Those are equivalent hydrogens. So for example, I'm going to draw our hydrogen here because we don't want to forget it. Okay. These hydrogens, and these hydrogens are all the same. They all have the same number of things nearby. They're all bonded to the same atom. They all have the same number of hydrogens on them. So that means all three of these are the same. So that's going to give one signal for those. And then this is different. So this is going to give our second signal. So this is going to have two signals. Okay. Let's look at this one here. I'm going to draw our hydrogen again. And we're going to have one signal for that hydrogen. This methyl group and this methyl group look the same because they have all the same attachments through our bonding, right? So this is going to give rise to a second peak. These two hydrogens are different than these or those. So this is going to give rise to our third peak. And then this last group here, that methyl group is attached to a CH2. That's not like these, that's different. So we're going to have a fourth peak. Okay, by looking at the different types of hydrogens you have, the different things they're connected to, you now know how many peaks you should see, the number of peaks you should see. All right, and let's do the last one here. These two methyl groups are the same. So these are going to give rise to one peak. Then we have a second peak here because that's different than the others. These two are probably the same because they look the same. They have the same attachment with the methyl group here, same attachment there. So those are probably the same. And then this last one right here is going to give us our fourth peak. So we can predict the number of peaks we should see from our system. So then we can also use that backwards by looking at how many peaks we have, and we can eliminate things that don't have the right number of different kinds of hydrogens. Okay. So spectroscopy is all about a puzzle. You look for evidence of things that are there, and you also look for evidence of things that aren't there, and you can do it. So let's look at these and see about equivalency here. This methyl group is exactly like that methyl group, so they're the same. It's going to give one signal. Anytime we have symmetry right here, those are going to be the same as those. They have symmetry, they are the same compound, they have one signal. This symmetry, oh, hand raised, yes.
Sorry, can you go back to the last slide really quick? Okay, so for the middle molecule for B, so why isn't that fourth group of hydrogens, that methyl group, the same as the other two methyl groups?
Okay, so if we looked at let's draw the connectivity. So let's look at number 4 here. So we have a CH3 connected to a CH2 connected to a C, right? Let's just do that part. That's for that one. Now let's do the one over here. We have a CH3 attached to a CH attached to a carbon over here. Okay, so if we look at the connection here, this one is connected to a CH. This one's connected to a CH2, so they're not the same.
Okay, that makes sense. Thank you.
Yeah. No, probably a lot of people had that question. So if I didn't clarify that. So you can basically, if you draw out this right here, you're looking for differences. Even like 2 or 3 bonds away, you'll see a difference. So you're looking for any difference in the chemical bonding. It tells you the number of equivalent hydrogens or number of peaks you should be getting. Okay. But again, symmetry, we have a plane of symmetry in this. And so you can actually cut it anywhere, and it's going to look, all of those signals are going to look the same. And again, we have a plane of symmetry, so those are all equivalent hydrogens as well. Okay. So each of these is only going to have one signal. Okay. Now, if we change anything in the system, we're going to have more signals, right? So instead of being that where we just had the chlorine that was attached to here, we move it over back here. So now we have 2 chlorines on here. So that makes a methyl group different than a CH group. Therefore, we're going to have 2 signals. Okay. Chlorine doesn't have a signal, only the hydrogens have a signal. Now, these two are the same because they're close to the carbonyl. These two are the same because they're further away from the carbonyl, but equivalent going around the ring. So we should see 2 signals in that compound. Let's go to this alkene right here. We have a chlorine. We're not going to see that in proton NMR, but we have a hydrogen next to chlorine, so that's going to be 1 signal. We have a hydrogen next to a methyl group, that's going to be another signal, and this methyl group is really far away. So that's going to be another signal. We're going to see 3 signals for this compound. Okay. And over here, we have the hydrogens on the alkene right here. So that's going to be a signal. We have the hydrogens next to the alkene, but we're going around a ring, so that these 2 are equivalent. So they're going to give the next signal. And then the last set of hydrogens is going to give our 3rd signal. Okay. So do we see what we mean by equivalent hydrogens and how to spot them? Okay. Again, that tells us number of peaks. Yeah. All right, we got 20 minutes left. Let's talk about shift. Okay, so the next thing we talked about was, we're going to talk about intensity later, but we're going to talk about position. And position is basically the time it takes to relax and when we hear that signal. And it changes based on what is attached to that carbon that has the hydrogens on it. Okay, so let's start with the simple one, the one we always call 0, TMS. It's 0 by definition, and we can start from there. The next thing we see is the thing that's going to relax the most is an alkane with 3 hydrogens on it. It's going to be the lowest signal we typically see at just below 1. If we take one of those hydrogens away and add a carbon, so if we only have 2 hydrogens on there, it's going to shift up. It's going to take longer to relax. And if we only have 1 hydrogen on there and 3 carbons here, it shifts up again. So we can actually see the difference between the end of an alkane, the middle of an alkane, and a branch point in an alkane. So here would be, like the end would show up here. This one would show up here. And then if we branched here, this one would show up here. So do them in different colors. So what I'm saying is that this methyl group, because it's at the end, is going to be that one. This CH2 is going to be there. And this CH is going to be in that position there. So that one molecule is going to have 3 different peaks for those 3 different positions. So we not only have peaks, we have positions. So we can look for building our molecule based on that. Now, the next thing we're going to see is that when we have a hydrogen on a carbon adjacent to a double bond, that shifts up again. Okay. Then the next thing we'll see is the alkyne hydrogen is in that same range. A CH3 bound to a benzene ring is going to be a little higher, or a CH2. See how it's additive? The CH2 is higher than it was for the CH3. We'll see that again and again. The more hydrogens you have, the faster it will relax. So the OH on there, the hydrogen on the alcohol, can be a lot of different places. And it can be a lot of different places because of its hydrogen bonding. That hydrogen bonding in its local environment is going to change where it does this spin. It'll also change in different solvents. So that's usually harder to see. Okay. Then CH2s next to an oxygen right here on this are in this 3 to 4 range, 3.3 to 4 range. The hydrogen on an amine actually also, because of hydrogen bonding, it's spread out wide. And once we get something bound directly to a carbonyl, we've shifted up to this right or just above 2. And we see that effect of having that carbonyl attached to it. That continues with our notice this is more like the carbon bonded to oxygen, but it's a little bit higher because that carbonyl does have influence. And this is a little bit higher because we have 2 hydrogens instead of 3. When it's bonded next to an electronegative atom, that shifts it up. But notice the trend follows electronegativity. Iodine is less electronegative than bromine, that's less than chlorine, that's less than fluorine. So our ranges increase here. Our OH for our alcohol on a benzene ring is higher and doesn't hydrogen bond as much, so it stays pretty close to that same location. So all of the alkanes are in this range. Now we're starting to see the alkene hydrogens right around 5. Alkene hydrogens right around 5. But aromatic ranges are above that. They're at 6 to 8. Because of resonance, and they're bonded differently, they are going to be higher to 8. And then the two highest peaks we see are aldehydes, which are right around 10, and carboxylic acids, which are 10 to 15. Okay, so that's position. That's how long it takes these things to relax. And so having a general idea of, oh, our alkanes are here, our alkanes are in the 1 range, but our alkenes are in the 4 range, we can start seeing alkanes and alkenes, and alkynes are in the 3 range. So we can start telling the difference between different functional groups by NMR as well. All right, now comes the hard peak, okay? Splitting, okay. Splitting is probably the hardest thing because it's hardest to kind of wrap your head around. But the idea is that we have hydrogens on an atom, okay? And those hydrogens are equivalent to each other, okay? So they don't split each other because they're exactly the same. However, on adjacent carbons, the number of hydrogens on those adjacent carbons will split the signal that we're looking at. So let's say we just have something like propane. So the middle, because it only has 2 hydrogens on it, is going to be shifted higher number position-wise because those 2 hydrogens are different than the ones with 3 hydrogens. Okay, the ones with the 3 hydrogens are going to be shifted lower. But these 2 hydrogens are going to be split by those 6 hydrogens that are not, but they're all within 3 bonds, okay? So when we think about the splitting, we want to look at the hydrogens within 3 bonds of the hydrogens that we're looking at, and that's going to tell us how many peaks we should see in there. Now, the number of peaks we're going to see is what we call the n+1. The 1 is for the protons we're looking at, that position we're looking at, and the n is the number of hydrogens, that non-equivalent hydrogens, that are within 3 bonds of those hydrogens. Okay, so the n is, we'll count up all the hydrogens within 3 bonds and add 1 for the peak we're looking at. So let's apply this. Okay, so in this case here, we have a compound here, and we have 3 chlorines on it. Okay, so that we have 2 hydrogens here, so that's different than the 1 hydrogen here. Okay, so we know we have 2 peaks, and we have 2 chlorines, and we only have 1 chlorine here, which means this is probably going to be shifted higher because we have chlorine, they're adding together to make it shift higher number. And now let's look at equivalency, okay? So I'm going to start with this this A hydrogen here, oops. Okay, so these 2 hydrogens make 1 peak because they're equivalent, okay? How many hydrogens do we have within 3 bonds of those hydrogens? So let's redraw it as hydrogen, hydrogen, chlorine, carbon, hydrogen, chlorine, and chlorine, okay? So we're looking at these hydrogens here that gives us 1 peak, and we have 1 hydrogen within 3 bonds. 1, 2, 3. Therefore, this peak is going to be split 1 time from that. So the number of peaks we are going to get in that position is 2. Okay. So this is going to be split by this 1 hydrogen. Okay. All right, now let's do this hydrogen here. Okay. So this has 1 peak because it only has 1 hydrogen, and all equivalent hydrogens would be the same anyway. And then if we look at the number of hydrogens within 3 peaks, we see 1, 2, 3, and 3. We have a total of 2 hydrogens that are within 3 bonds of this hydrogen. So our n is going to be 2 plus the 1 peak, which means we should end up with 3 peaks. Okay. So that's how we do peak-to-peak splitting. Don't worry, we're going to do a couple more. So if we look at our end here, we see that the 1 hydrogen here the two hydrogens are split once, giving us two peaks, and I'll blow one up in a little bit so you can see. And that one hydrogen was split into three peaks, or what we call a triplet. So we have a singlet is a single peak, a doublet is two, a triplet is three, a quartet is four, etc. Okay, so let's do a couple more splitting experiments just to make sure we have it. No. All right. So we're going to look at this molecule here and predict what we should see, okay? Based on what we know so far about position, splitting, and equivalency, okay? So the first thing we're going to see here is that these two hydrogens here are different than the other hydrogens because of their proximity to a chlorine and a carbon, and these are equivalent. So we have the blue hydrogens here are one type of peak, okay? These hydrogens here are equivalent because if we look at where they're bonded, they are different than the other two, and so this is going to be our second peak we see. And then the last one, because we have three hydrogens on it, that's different than the other two that only had two. So this is going to give rise to our third peak. Okay. Now let's predict position. Okay. Position is, this is going to be, these ones right here are close to a chlorine. We saw that chlorine shifted up the highest. So this should be the highest number. So we're going to say in the order of where we see them on the board, we're going to have one. These hydrogens are closest to the chlorine compared to these hydrogens, so they're going to be shifted next. So they're going to be two. And then the third one is going to be on there. So the third one is going to be the closest to zero. The second one is going to be next, and the third one is going to be the furthest away from zero, just by position. Okay. Now, let's think about intensity. What intensity, what kind of curves should we see under there? Well, all we have to do is count the number of hydrogens we have right here. So that means peak one should have two hydrogens. Peak two should have two hydrogens. Peak three has three hydrogens. Okay, so we have number of signals, we have intensity of signals, we have position of signals. Now let's do the splitting, okay? The splitting goes by our n+1 rule. So let's look at peak number one, okay? So this is a single peak, and how many hydrogens do we have within three bonds? 1, 2, 3, 1, 2, 3. The chlorine doesn't split, and these are equivalent. So we have two hydrogens that are within three bonds of this first peak. So that means our first peak should be 2, which is our n+1 is 3. So we should have a triplet. And notice when we have a triplet, the middle is always higher than the two side ones. It's just how it lays out. So now let's look at the one in the middle here. We have these hydrogens are, of course, equivalent, but now we have 1, 2, 3, 4, 5. We have 5 hydrogens that are going to be splitting this peak. So we have n+3, which is 5, plus 1. That's going to give us 6 peaks. So let's see, 6 peaks. It's going to look something like that. Does everybody see where the n is coming from and why we add 1 to it? 1 is for the peak itself, and then we add a peak for each hydrogen we have. So that's 1 peak split into 2, split into 3, split into 4, split into 5, split into 6. Okay, and let's do our last one. Okay, so we have these 3 hydrogens are equivalent, and so we only have 1, 2 hydrogens there. So that means our n+2 is going to be 3. So we should see a triplet for that peak. Okay, so we've predicted where they should be, how many hydrogens we should have, what they should look like as far as the shape of the peak. So let's go see if we're right. Okay, so let's look at our peak here. Okay, so the cool thing is we have positions right here. This is the one with the CH2Cl. This is the CH2, and this was the CH3 at the end, okay? So we have positions are in order. We have 2 hydrogens, and 3 hydrogens. So we have the number of hydrogens, or the intensity, correct. We have a total of 3 peaks. So we have the number of peaks correct. Now let's look at our splitting. Okay. Our splitting here, we have a triplet. And let's see, 1, 2, 3, 4, 5, 6 peaks. So we have a sextet. And 1, 2, 3, we have 3 peaks here. So we got the splitting right. We got the intensity right. We got the relative position correct. And we got the number of peaks correct. So we can predict an NMR spectrum. Now, you can also go backwards. You can say, what do I have in the NMR spectrum? And then you can build your structure from there. Okay. All right. Let's see if I got a couple more examples on this. Yes. All right. Let's predict the number of signals on these in our last 5 minutes so we can get this really, really down. The first thing we need to do is make sure things are equivalent or not equivalent. Okay. So we have a CH3 next to a carbonyl. So that's different than this CH3. And this is a CH2, so that's automatically different. So we're going to have 3 peaks. Okay. So if we have 3 peaks, we have, let's start looking at our splitting now. Okay. Let's start with this number 1 here, right here. And how many hydrogens do we have within 3 peaks? We got hydrogen there. We have 0 hydrogens within 3 peaks because the carbonyl does not have any hydrogens on it. So that means we're going to get 1 n plus 1, which is 0 plus 1. So we're going to have 1 peak. And so we're going to have a singlet on that one. Okay. Let's do the other methyl group now. Other methyl group here. It's got 1 and 2 hydrogens within 3 bonds. So this is going to be a triplet. 2 plus 1 is equal to 3. It's going to give us a triplet. Okay. Now let's do this last one right here in red. We have 2 hydrogens here, so that gives us 1 peak. But then we have 1, 2, 3 hydrogens there. So that's 1 plus 3, which is a 4, a quartet. So we should have a singlet, a triplet, and a quartet just based on the splitting pattern. Do we all understand that? Okay. Now I'm going to throw you a curveball. We're going to have something that's symmetrical. Okay. When it's symmetrical like this, these are equivalent to each other, and these are equivalent to each other. So we're going to have 2 peaks. Okay. But we still have to analyze for our splitting. So we had 3 protons next to 2 protons. So these 3 protons are 1 signal plus 2 protons is a triplet. So let's look at the other side now. This right here, we have 2 protons that gives us 1 signal, but it's next to 3 right here. So that's going to give us a quartet. Okay. Do we see where the peak splitting is coming from? The number of hydrogens that are within 3 bonds of that peak you're looking for. So now let's do this one right here, but I want to redraw it so we make sure we get it. I want to redraw it to be this, CH3, CH3, H, CH3. Okay, so now let's look for equivalence real quick. And this is my last slide, so 3. There are no hydrogens within 3 bonds right here, so this is going to give us 1 peak. Okay. This methyl group is equivalent to that methyl group, and they have 1 hydrogen next to it. So that means this is going to give us 2 peaks. This hydrogen is different than all the others, and so it's going to have its own peak. But now it's next to 3 on this one and 3 on that one, so it's 6. So that means we're going to have 7 peaks right here. So that's going to heptet because it's next to 6 other hydrogens, plus itself is a total of 7 peaks. All right, that brings us to our 1220. So if you have questions, go ahead and stay behind. If not, go ahead. I'll stop recording and I will see you on Thursday.